Section 4.2, the mean value theorem. Now this section it's kind of a standalone section, getting away a little bit from what we were talking about in the first section where we were looking at locations of extreme values, turning points, maximum and minimum values of a function. We're going to get back to that in the next section in 4.3 and start looking at how we can actually use the derivative to help us find those values. But in the meantime, in the middle of that, we'll talk about this mean value theorem. And actually, there's a couple of theorems in this section that we're going to mention, but it still involves the derivative, so we're still keeping with that theme of what the derivative tells you about the shape of the graph of a function or function values as they relate to each other. Now, again, I think this is a pretty straightforward section. The two theorems that we're going to talk about, Rolle's theorem and the mean value theorem. But I guess the biggest issue I have here, the confusion comes in as usual, is just keeping them straight, not getting them confused in terms of what Rolle's theorem tells you and what the mean value theorem tells you, because they're very similar, okay? And it turns out that Rolle's theorem is actually just a specific case of the mean value theorem, so they're very similar to each other in what they say, so it's very easy to get them backwards or confused. So be careful there. It's like anything else. You have to know how each one or what each one says individually. Don't cross the wires between these two. So, well, what are these all about? Well, let's start with Rolle's theorem, and then we'll talk about the more general mean value theorem. Rolle's theorem says that if we have a function f that satisfies the following requirements, that first, f is continuous on the closed interval from a to b, given that f is also differentiable on the open interval from a to b, and given that f of a equals f of b, so in other words, the value of the function at the endpoints of the interval are the same, then we guarantee you that there is a number, call it c, somewhere in that interval from a to b, such that f prime of c has to equal 0. Now again, what is this saying? These requirements are specific. I must guarantee or verify that each of these requirements is met in order to use Rolle's theorem, or we say in order to verify the conclusion of Rolle's theorem. Now, you don't have to do anything fancy to prove them, at least the first two. We've talked about continuity over an interval. We've talked about differentiability over an interval. And so if I have a function that I can just by observation tell you is continuous over the closed interval, now do be careful here. Continuity, remember, we can talk about continuity at the end point of an interval. We can't talk about differentiability at the end point of an interval because we don't know what's happening outside the interval. But we did talk about continuity at the end point. You could be continuous from the left or from the right. So these are two statements that must be made with respect to our function, of course, provided that they are true. That f would be continuous first on the closed interval from a to b. F is differentiable on the open interval from a to b. So again, always differentiable on an open interval. We never talk about differentiability at the end point of an interval. Simply the fact that it's differentiable at every point in the interval. Now, for Rolle's theorem, we also have a third requirement, that f of a has to equal f of b. So we do it easily to show that. We plug in the endpoints of the interval a and b, and if we get the same function value, then we've met the three requirements to use Rolle's theorem. Those are the three hypotheses, we call them. So the question might say, verify the three hypotheses of Rolle's theorem, and then find a value c that satisfy the conclusion. And the conclusion for Rolle's theorem says that if the three requirements are met, then we guarantee you that there is at least one number c, there could be more, in the interval from a to b where the derivative is equal to 0. Or in other words, like we know from our graphical observation, the derivative is 0 where you have a horizontal tangent, right? So of course you could have a horizontal line. I'll give you a few examples underneath that, general examples of graphs. you could have a horizontal line where at every point the derivative is 0. Or you could have something like the other three, where you have those turning points like we've talked about. Now notice again in each case, the endpoints are the same. F of A and F of B are the same value. And there is at least one number C somewhere between those two where F prime of C equals 0, or where you have that horizontal tangent. Now notice, like in the last case, there's 2 points where that happens. So it doesn't say anything about how many, it just says that there's at least one. There could be more. Okay? So for example, let's let f of x be the function x cubed minus 3x squared plus 2x plus 5, and we're looking at this function on the interval from 0 to 2. So like I said, here's a typical question. Verify that the function satisfies the 3 hypotheses, and then find all numbers C that satisfy the conclusion of Rolle's theorem in this case. So I'll have to be specific as far as which theorem we're talking about. So first, do we have continuity over the interval? Well, I know that this function is continuous on the interval from 0 to 2 because it's a polynomial function, which, remember, and this comes from previous discussions, polynomial functions are continuous everywhere. That's one of those functions who said that they're continuous on their domains. And since the domain of the polynomial function is all real numbers, then it is continuous everywhere. And so more specifically, it is continuous on the interval, the closed interval from 0 to 2. That is a statement that you must make. The second statement, second requirement, is that the function is differentiable on the open interval, in this case from 0 to 2. And again, that's going to be true because it's a polynomial function, which again, previous discussion, we know is differentiable everywhere. So there's nothing that you have to do to formally prove those. We can make it by observation. We already have theorems that establish those facts. But then for Rolle's theorem, we also have to look at the endpoints and verify that the function value at each endpoint of the interval is the same. And if you plug 0 into that function, so I'm plugging in f of 0, the left endpoint. If you plug in 2, I'm plugging 2 into our function, the right endpoint. In both cases, you will get 5, so those function values are indeed equivalent. And so once I state the 3 requirements, then let's find the values for C, or values for x, and I don't care if you use x or c. I'm not going to split hairs with you on that. Find your c values, find the values for x where the derivative is 0, because by having those 3 requirements met, we guarantee you that there's at least one. There could be more than one, okay? But we guarantee you that there is at least one. So set our derivative, find our derivative first of all. So f prime, again, nice little polynomial. So power rule, 3x squared minus 6x plus 2 is our derivative. And then we'll set that equal to 0 and solve that equation. Now in this case, that's not a factorable polynomial, so we had to use quadratic formula. So that's all I did there. I ran 3x squared minus 6x plus 2 through the quadratic formula with a equals 3, b equals -6, and c equals 2. So that's where all of this came from. Now, whether or not you simplify that radical 2 square roots of 3, because you end up with square root of 12, right? 36 minus 24, which is 2 square roots of 3. I don't really care if you simplify that or not, because we're going to approximate it to see exactly what those values are. Well, approximate to see exactly, that's kind of contradictory terms, but we're going to approximate the radical so that we can get an idea of what the values are, all right? So that's all I'm doing there, and if you approximate the radical and then just plug those values in, you're going to get, on the positive side, you get approximately 1.6, and on the negative side, you get approximately 0.4. And then I went ahead and just plugged those values into our function. All right, so we're looking at, and again, whether or not you actually identify the points, we're asked to verify the hypotheses and then find all numbers C that satisfy the conclusion So really, that's all you would need to give as far as your final answer. So x is approximately 0.4, x is approximately 1.6. Those are your C values, all right, that satisfy the conclusion. So I went ahead and found the points themselves. I plugged them into our function, and we got the points 0.4, 5.4, 1.6, 4.6. But again, it's all about the x coordinates. It's all about the C values. Okay? And I thought there's something else I wanted to say there, but I guess not. Oh, I know what it was. So again, like we said, the theorem guarantees us that there's at least one C value. Notice in this case there are two. Now both of those points are located in our interval, right? So once you do find the values that satisfy your conclusion, make sure they're actually in the interval. So first of all, they should be, or at least one of them should be. And in this case, there are two values, 0.4 and 1.6, that are both in that interval. Okay? But that's all that is. I mean, there's nothing new there. You're just differentiating the function, finding where the function is equal to 0, or the derivative, I should say more specifically, is equal to 0 to satisfy the conclusion of your theorem, of Rolle's theorem in this case. Now, I told you that Rolle's theorem was a specific case of ultimately this mean value theorem. So what the mean value theorem says is, again, provided that f is a function that satisfies the following conditions. Now notice the two conditions here. They're exactly the same as the first two conditions of Rolle's theorem, or our hypotheses of Rolle's theorem. So provided that f is continuous on the closed interval from a to b, and provided that f is differentiable on the open interval from a to b. So notice there is no third requirement, that the function values are the same. So if that's not necessarily true, then provided that the first two statements are true, then here's what we can tell you. Again, because of continuity and differentiability, we know it's continuous, we know the derivative exists, we can guarantee you that there's at least one number c in that interval from a to b, such that f prime of c, right, so our derivative at c, is equal to f of b minus f of a over b minus a. Well, what is that? That's the slope of the line passing through the points af of a and bf of b, right, which are the endpoints of your interval. Right? We're on the interval from a to b. So in other words, f prime of c, remember that's the slope of our tan line? So we're saying that there is a tangent line that has the same slope as the line passing through those two endpoints, or that's what we previously called the secant line, or a secant line for that function. And so we're saying that somewhere in the interval there's at least one value c, one point in the interval between a and b, where the slope of the tan line is the same as the slope of the secant line passing through the endpoints. Or that we could also say that those two lines are parallel, right? Because they have the same slope. Now that also works with Rolle's theorem, because Rolle's theorem, the one that we looked at first, had the requirement that f of a equals f of b. The only thing that added to it was it allowed us to say then that I have some value where the derivative is 0. But this also holds true for the mean value theorem, because even though the endpoints are the same, great, fine, wonderful, notice if I were to draw the secant line, right, through the endpoints, just simply means that do that again. It simply means that the secant line is also going to be horizontal, right? So when you draw the secant line through the endpoints, just because of the fact that they are the same function value or have the same function value, you have a horizontal secant line, which is again also true for the tan line, because that's where the derivative is 0. Okay, so even with this one, you would have a horizontal secant line passing through those endpoints. Okay, so that's why I say Rolle's theorem is just a specific case of mean value theorem. Okay, and that it simply means that they end up being horizontal. So the mean value theorem is the more general case where whether or not the endpoints are the same or not, provided you have continuity and differentiability over the interval, we guarantee you that there's at least one point where the horizontal, where the tan line and the secant line passing through the endpoints has the same slope. So really this just comes down to an equation that we'll solve. We'll set f prime of c, so we'll find our derivative and set it equal to the slope of the tan line, f of b minus f of a over b minus a. And then we'll solve that equation. All right? And so like I told you before, whether you call it c values, x values, I don't care. All right? We just want to find the values of x that satisfy that equation. So here's our example. I've got the function f of x equals 3 over x plus 2, x over x plus 2 on the interval from 1 to 4. Now notice this function is not polynomial. It is a rational function. So we do have to, at least check to make sure that we are continuous and differentiable over our interval. What's the domain of that function? Well, that would be undefined where x equals -2. So the only value that's not in the domain of that function f is x equal to -2, but notice that is not in our interval. Our interval is from 1 to 4. So from our previous theorems and what we know about this type of function, rational functions are also continuous and differentiable over their domains. All right. And since -2, the point of discontinuity, is not in our interval, that's fine. Over this interval then from 1 to 4, we do have continuity and differentiability. So again, the same type of question I had previously. We're going to verify that we meet the hypotheses of the MVT, mean value theorem. And then we find all numbers C that satisfy the conclusion. So again, because of the type of function that we have in previously existing theorems, we know that this function is continuous everywhere except at x equals -2. So I would say, and I'm going to be more specific here, I will say that this function is continuous on the interval from 1 to 4. The closed interval from 1 to 4. And again, we know that the function is differentiable everywhere except at x equals -2. So again, this function is continuous on the open interval from 1 to 4. So again, I expect you to make those statements. All right. And it's never going to be a question of whether it's true or not, because the type of function that you're going to be given, it's not going to be a question of can you use Rolle's theorem or mean value theorem. It's going to be a question about actually finding the values. Now, in your homework, there will be a couple of questions that'll address situations like that. So, they'll ask you something like, explain why Rolle's theorem doesn't apply, or explain why mean value theorem doesn't apply. So we know the requirements, so it simply means that one of those requirements is not being met. You just need to show which one. Okay? All right, so provided we have the requirements, and again, that should be stated. Now that's it for the mean value theorem, right? That's the only 2 requirements. So then the conclusion tells us that there is at least one value for C or X, again, whichever you prefer, where f prime of C or f prime of X is equal to f of B minus f of A over B minus A. So we're just going to set up our equation, right? What is f prime at C? What is f of B? What is f of A over B minus A? And so A in this case is 1, our left endpoint of our interval. B is 4, the right endpoint. So f prime of x, and since f of x equals x over x plus 2, that is going to be a quotient rule, right? So again, it's all about finding the derivative of the function, whatever type of function you have. So x over x plus 2, the derivative would be our low d high. So low is x plus 2, d high is the derivative of x is 1, minus high d low. High is x, derivative of x plus 2, again, is just 1. So there's our low d high minus high d low over low squared. I'm not going to reinvent the wheel every time now. So you should be able to differentiate that basic rational function. And so then by simplification, we do have x minus x, so I just end up with 2 over x plus 2 squared, and that's f prime of x. F of 4, f of 1, right, plugging in our endpoints, so f of 4, if you plug that into our function, now again, that's going back into the function. So that would be 4 over 4 plus 2, or 4 over 6, or 2/3. If you plug in 1, you've got 1 over 1 plus 2, or 1/3. And then we're just going to plug everything into our equation on the left. So there's f prime of c, or f prime of x if you prefer. Again, I don't care which you use. That is equal to f of b minus f of a, f of 4 minus f of 1, over 4 minus 1. And then from there, it's just solving the equation. That's all this is. All right, so there's the left side. I just left that alone, 2 over c plus 2 squared. The right side, 2/3 minus 1/3 is 1/3. And then 1/3 divided by 3, or 1/3 times 1/3, is 1/9. And then what I typically do, like I said, when I'm solving equations that have fractions, I just clear the denominators. So in this case, you could actually use cross multiplication. If you remember proportions, fraction equal to a fraction, and you can use cross multiplication to simplify, or to rewrite the equation, I should say. So I've got 2 times 9, or 18. I've got 1 times c plus 2 squared, which is c plus 2 squared. So there's our equation. And then again, I'm going to use square root property because I do have c plus 2 squared. So I'm going to do the square root of both sides. So c plus 2 is plus or minus square root of 18. Solve that for c, and I've got c equals negative 2. I'm going to have to subtract 2. Plus or minus the square root of 18, which would be 3 square roots of 2. And again, I don't care about simplifying the radical per se, because we're going to approximate those values anyway to make sure that they're actually in the interval. Okay. So negative 2 rather, plus square root of 18, or 3 square roots of 2, gives you approximately 2.24. And negative 2 minus square root of 18, or 3 square roots of 2, is going to give you approximately negative 6.24. So just like with that previous example that we did with Rolle's theorem, we do get 2 solutions here. We do get 2 c values. But if we go back to our interval, again, remember the interval here is 1 to 4. Right? So that's the interval over which we are asked to find our c values. So I'm only including approximately 2.24 as my only solution, or value for c that satisfies the conclusion of the mean value theorem in this case, because negative 6.24 is not in the interval. Right? And that's a perfectly good value for c. It also, meets or would be a point on the graph where the slope of the tan line would be the same as the slope of the secant line through the endpoints. But it's not a point in the interval. So like I said earlier, you only care about the points that are actually in the interval, because sometimes you find others. Okay? All the theorem says is we guarantee there's at least one in the interval. There may be more than one, but there may be some outside of the interval as well. Okay? But again, that's a typical MVT question. There's nothing new there in terms of what we're doing as far as finding a derivative and solving an equation. So that's old business. These other couple of statements is another theorem and corollary. These are just some additional observations that you can make about the relationship between functions. Kind of an extension again of what the mean value theorem tells us. We also have a theorem, and this kind of goes back to what we talked about with Rolle's theorem, actually, which we said was a specific case of mean value theorem. That if the derivative is 0, if f prime of x equals 0, for all values of x in the interval from a to b, then we know that our function would be constant on that interval. Because remember, if the derivative is 0, that's where the tan line would be horizontal. And if it's 0 for every value in the interval, for every number between a and b, right, that would be kind of this case that you're dealing with. So every point in the interval from a to b, the derivative there would be 0. So you have a constant function, or in other words, you have a function whose graph is a horizontal line. Corollary, we always have these fancy words in math. You have theorems, and then you get corollaries coming from theorems. You also see words like postulates and lemmas and all these things, but they're basically just extensions or observations that can be made based upon what you know from the theorem. So a bunch of little fancy words. But what this corollary tells us is that if the derivative of two functions, f of x and g of x, are the same, so if f prime of x is equal to g prime of x, for all x in your interval from a to b, right? So now above that, the theorem says that if the derivative is 0 for every point in the interval, then the graph is a horizontal line, right? It's a constant function. Here we're comparing two functions. We're saying that if the derivative of f and the derivative of g are the same at every value of x in the interval from a to b, then what this tells us is that f minus g is a constant. Or in other words, the difference between those two functions would have to be the same. So it's kind of like the fact that if they were both linear functions, remember, if the derivative is the same, the slope of the line would be the same, which means they were parallel. So in the case of linear functions, so like if f of x and g of x are both linear and they had the same slope, they're parallel lines, right? But if they're not linear, the idea is still the same in that the slope of the curve at any given value of x is going to be the same for both functions. So they're quote unquote parallel graphs, right, in the sense of having the same derivative at any given value. We call them families of functions or families of curves. So a curve like y equals x cubed minus x plus 4, y equals x cubed minus x minus 7. Notice the only difference between the two is the constant, right? So in other words, you should be able to take your function f of x and express it in the form of g of x plus a constant. If you remember back to your algebra when you talk about like transformations, remember transformations of curves, so something like this, right? A set of axes. And let's say I got a function f whose graph looks like this, right? If I have a function g where the derivative at every point on the graph of g is exactly the same as that of the graph of f, then I could have something like this. I can draw this half decent. Let me try that again. All right. So basically, you can take the graph of f and shift it up or down. Remember transformations, if I take f, say, and shift it down a certain value, you're going to match up with the function g, right, if you just shift this thing down. But at any point on the graph of f and g, the slope of the tangent line is the same. So it's the same idea as parallel lines, but it's parallel curves. Okay. Now, again, that's not the main interest in this section. It's just kind of an extension of the observations we're making. I'm mainly interested in Rolle's theorem and mean value theorem and what those say and proving them given two functions, or given a situation where they don't apply, why not? Right. So again, you'll have some questions like that in your homework. So a little bit of a different section, but I think ultimately it's a pretty straightforward use. You have to keep them straight. Don't get the two theorems confused. That's what I see happen all the time. And that's it for that section.